Welcome, my dear students, to the online lecture series of the subject Mechanical Solids. So, this is the sixth lecture of this course. And in the last lecture, we discussed about stress at a point. We know what is stress at a point. Stress at a point is defined as the totality of all stress vectors acting on every possible plane passing through that point. So, that is stress at a point. Then we define the stress tensor. We have infinite number of planes through a point P, and out of this infinite number of planes we have infinite number of stress vectors, and this set of stress vectors acting on every plane passing through that point describe the state of that state of stress at that point, and that is called stress tensor. And we define a stress matrix. In that we have 9 components. By applying cross shear, we can reduce these 9 components into 6 components. Then for a plane stress or plane strain condition, we can reduce again these 9 components into 4 components. Then we discuss about the stress components on an arbitrary plane, the Cauchy's formula, and using these equations of Cauchy's equations, we can calculate the stress on any arbitrary plane in terms of the direction cosines and the stress components in a three mutually perpendicular planes. So that all what we are discussed in the last class. Now in this class we will discuss about strain. So we know in mechanical solid these two terms are very important, stress and strain. So when we apply a particular external force on a body, there will be a stress or internal force or internal resistance will be offered by the body, and corresponding to that internal resistance there will be a stress, and there similar to the stress or for a body subjected to external force, there will be some effects also. When we apply some external force, there will be some effects on the body, and that effect is nothing but deformation. Okay, so we already discussed that in mechanical solids we deal with the body which is deformable. Naturally, all bodies when we are dealing in engineering is a deformable body. Okay, so here if we apply a particular amount of external force, there will be some deformation. Okay, naturally, no material is perfectly rigid. Okay, so under the action of the external force, this material undergoes deformation. For example, in this case, for example, see this material. See this material. In this material, when I apply external force, there is a deformation for this material. Okay, there is a deformation. And this deformation can be we can see this deformation because very small amount of force, the deformation is quite large in this case. But in case of materials like steel, for example, take this material steel. So material like steel or concrete or brass or copper or aluminum, if we apply this much amount of very small force, we cannot see any type of deformation. But the deformations are very small, so that there will be deformation, and the deformations are very small, but actually we cannot see that deformation by our naked eye. Okay, but there is a deformation when we supply, even when we supply a very small amount of force, there will be some deformation for this body like a steel or concrete body. Okay, but if we use any sponge material or this type of clay material, this deformation is visible. Okay, so in any body, naturally in any body, all bodies are deformable body. So when we apply an external force on this body, there will be some deformation. Okay, then next question is, how can we measure this deformation? how can we measure this deformation? For example, if you take a bar with the length L, a bar with the length L, and applying a force F, okay, and taking another bar with the length length L1. This is length L1 and this is length L2. Okay, this bar length is different, and applying a same force F. Okay, same force F. And here I am applying same tensile force. Is this deformation is same? Here the force is same, and but the length or diameter is different. Then the deformation will be same? No chance. So the deformation is depend upon the length or size of the body. It is depend upon the length or size of the body. So we cannot measure deformation directly because this deformation is depend upon the size of the body. So if you measure, for example, for a particular body, uh, here I am applying a force F, the deformation is equal to delta L1. So if we apply same force on another body with a different size, the deformation will not be delta L1. So there is no direct relationship between these two deformations. Okay, so we need to specify the deformation with respect to the size of the body. With respect to the size of the body. So that quantity is called strain. That quantity is called strain. Okay, so the deformation of a body under a load is proportional to its length. Is proportional to its length or its size. Okay, so here we represent the deformation in terms of the length or size of the body. So that to study the behavior of a material, it is convenient to study the deformation per unit length of the body than that of the total deformation of the body. Then here this is total deformation of the body, but it is more convenient because if we describe this deform or define this deformation with respect to unit length, then we can apply that quantity for all bodies. But here we cannot apply this delta L1 for this body because the length is different. So here the deformation also will be different. So we use a term called strain, and this is nothing but it is the deformation per unit length. Deformation per unit length. Okay, so that is the importance of the term strain. So we can directly measure deformation, but the main problem is this: when we apply particular force, the deformation vary with the size of the, even if this force is same, the deformation vary with the size of the body. So for generalizing this deformation for all body, we use this term strain. So strain is equal to deformation per unit length. Okay. So the deformation, it may be elongation or contraction uh, of the length of the body per unit length of the body is called strain, and we represent this letter epsilon for representing a strain. Epsilon is used to represent a strain. Okay, and strain also similar to stress. Strain also two types: linear strain and shear strain. In case of stress, we have normal stress and shear stress. Similarly here, linear strain and shear strain. Okay, next we will discuss about linear strain. Linear strain. So for that, I am taking a bar element. bar element with the length L, I am applying a force F on this bar element. So when this bar element of length L subjected to external force, what happened? Its length will increase because this force is a tensile force. So the length will increase. Okay. And what is the change in length? Final length of the body after deformation? L plus delta L. L plus delta L under the external force. Okay. Then the strain or linear strain epsilon is equal to change in length by original length. Change in length by original length. That is equal to what is the change in length? Final length minus initial length. So L plus delta L minus L. That is the change in length. By original length is L. So this is equal to delta L by L. Delta L by L. So that is the linear strain. Okay. So the deformation of the body under a load is proportional to its length. And here in this bar subjected to direct stress. Here this is a normal stress or direct stress, and the stress in the bar will change its length. There will be elongation for this bar, and the strain is equal to epsilon is equal to delta L by L. Okay. And this is the measure of the strain is nothing but it is the measure of the deformation of the body or material. Okay, so when we apply external force, there will be some stress developed on a body. And what is the effect of this stress or external force? The effect of stress or external force will be a deformation, but we are not directly measure this or directly indicating this deformation. We are not indicating this deformation directly, but we indirectly in terms of strain we indicate this deformation value. Okay, so we measure the deformation in terms of strain. So this is the reason. Okay, if we change the size of the body, the deformation also will vary. So we measure the deformation in terms of strain. Okay, that is the strain on a body. Next one is shear strain. Shear strain. So similar to this shear stress, we have shear strain. Shear strain. Okay. So similar to shear stress, shear strain is also when a body is subjected to shear stress. For example, consider a cubical element or cubical body. Okay, this is subjected to a shear force or shear stress, tau xy, a pure shear, because it is only subjected to shear force or shear stress. That is why it is called pure shear condition. So this body is subjected to shear force or shear stress. This is Z, X, Y. Okay. And when this body is subjected to this type of shear stress, what happened? There will be a change in shape of the body. There will be a change in shape of the body. What will be the shape after deformation when it is subjected to shear force? Oh, sorry. When it is subjected to shear force, this will be the change in shape of the body. Okay, so here the tau xy is acting. and here also tau xy is acting. Okay, and here we can see initially this line, two lines are vertical 90°. Okay, initially these two lines are vertical, but after deformation, when we apply external shear force, what happened? It's deformed, and this is a rhomboid shape, and its angle is changed from this vertical position to or the angle between these two faces are vertical or 90°, but here it is changes from vertical by an angle gamma xy is changed by an angle gamma xy, and similarly this 90° changes to what? 90° or pi by 2 in pi by 2 minus gamma xy. This will be pi by 2 minus gamma xy. Initially it was 90°, but after application of external shear force, this changes to a rhomboid shape. A cube is changes to a rhomboid shape, and its angle is changes from 90° to 90 minus pi by 2 minus gamma xy value. Okay, so here we have two angles are formed by the four faces under shear stress, and here we can say the pi by 2 is reduced to in between these two faces, the pi by 2 is reduced to pi by 2 minus gamma xy. Okay, but here what happened? Here what happened? In this angle it is increased from pi by 2 plus gamma xy. Now it is here it is pi by 2, but here it is pi by 2 plus gamma xy. Okay, so this deformation is because of the shear strain application of when we apply shear stress or shear force, the completely it's deformed, its shape is changed. But in the previous case for linear strain, there is no change in shape. If the bar is initially a rectangular bar, after deformation also it is a rectangular bar, but its length is changed. But here the entire shape is changed, or we can say this type of deformation is a distortion of shape. The shape, entire shape is distorted. Okay, so that is very important. In case of shear strain, the entire shape is distorted. So here this angle gamma xy, the small angle gamma xy, that is expressed in radians, defines the shearing strain corresponding to xy direction. So this gamma xy is the shearing strain corresponding to x1 and y direction. So I will show the front view of this cube. So this is the front view. Initially, for example, I am fixing this edge. This edge or this face is fixed. Okay, so we can see this is the front view A, B, C, D. Here the shear stress is acting. Shear stress is acting. Okay, this end is fixed. So when it's subjected to shear stress, what happen? This will be the front view after deformation. After deformation, this will be the front. Okay, and here this there is no change in A and D because the bottom face is fixed. Okay, bottom face is fixed. So there is no change in A and D, but B is changed from B to B dash. So this is new position B dash. C changes from C to C dash. Okay. So this block is, or the front view of this cube will change and there we can see there is a change in shape also. The shape of the cube also changed. Okay. So when the deformation involves a reduction of angle formed by two faces oriented respectively in gamma xy towards positive x and y axis, then we can say that is positive shear strain. Okay, positive shear strain. So if it is oriented, that means the angle is reduced in positive towards the positive x and y direction, then we can say that is a positive shear strain. So what is shear strain? Shear strain is defined as the change in right angle of the element measured in radians, and we know the strain is a dimensionless value, because the numerator and the denominator has same unit, so it is a dimensionless value. Okay, so gamma xy, this gamma or gamma xy is the shear strain. Shear strain is the gamma xy. Okay, and here from this figure we can say what is, if we join this edge, this is B and this is B dash. What is tan gamma? Tan gamma. What is tan gamma? Tan gamma equal to, from this triangle, initially it is B and this is changes to B dash. So tan gamma is equal to, opposite side is B dash, B dash, and this side is AB. AB. Okay. And here the gamma xy value is very small. Gamma xy value is very small because under shear force this distortion will be very small, so we can say gamma xy is very small. Then we can assume this tan gamma xy as gamma xy. So gamma xy equal to bb dash by ab. bb dash by ab. Okay. So that is the measure of shear strain. bb dash by ab is the measure of shear strain. So gamma tan gamma xy equal to gamma xy. We can assume that tan gamma xy is equal to gamma xy. So this is about shear strain. Next one is superficial strain. In case any deformation for area, then we use superficial strain, that is dA by A, change in area by original area. Commonly we are not using this term, but dA by A is the superficial area. But another term is important, volumetric strain. Volumetric strain. Volumetric strain, that is the change in volume by original volume. Change in volume by original volume. So that is equal to delta V by V. That is called volumetric strain. So we have the linear strain, that is delta L by L or delta D by D. If it is a diameter, delta D by D or delta L by L. Okay. And area strain, delta A by A, or superficial strain is delta A by A. And this volumetric strain is delta V by V. Change in volume, change in area, change in diameter, change in length with the original dimensions. DL, original length, original diameter, original area, or original volume. So this is the strain in different terms. Okay. Next we are going to derive a relationship between this displacement and strain. Strain and displacement. Okay. So here in this bar, so this is displacement or displacement and the displacement gradient. Displacement gradient. Okay, so I'm considering a bar with the length dx, so the bar is AB, and this is in the xy plane, and the coordinate of A is in the x direction is x. We only considering the x coordinate. So this is at a distance. The point A is at a distance x from the origin. Okay. Then when we apply external force on this body, two different types of displacement can happen on this body. Two different types of displacement. The first one is if we apply a particular force on this body. Okay. If we consider this body as a rigid body, what happened? When we apply an external force, is move in the direction of force. Okay, it moves in the, or it displays in the direction of force. So there will be a, or if we try give a rotational force, then it starts to rotate in that direction. So there will be a displacement in the direction of external force. So here we consider that is a rigid body. So that is the rigid body motion. So first one is rigid body motion. The second one is deformation. When we apply a force on this body, the material will be deformed. So the deformation also a displacement, because there will be a change in position for the body. Okay, there will be a change in position for the body. So the deformation also will happen on that body. Now deformation may be a normal deformation or shear deformation. Okay, so these are the two type of displacement or change in position when we supply an external force. So I am going to apply these two forces on this two type of deformation on this bar. Okay, so what happened to this body when I apply an external force on this body? This body will move by a distance. Okay, by a distance. So this is the new position of the body. New position of the body. This coordinate of this point is, you can say, x plus u. Okay, and the position is a dash. A changes to a dash. So this is x plus u. So this is because of displacement, the rigid body motion. Rigid body motion displacement. Okay, so the position changes from, because of the when we apply an external force, it changes from point A to a dash. And second one, this end, what is the coordinate of this end? The coordinate of this end will be, here this point is x plus u, so x plus u plus dx plus, because this distance dx is the initial length, dx plus, there will be a deformation for this bar under the external load. A deformation for this bar under the external load, that is dou u by dou x into dx. Okay, dou u by dou x into dx. So this is the coordinate of this b dash. Here this is the coordinate of a dash. So the distance will be the initial distance. Already there is an initial distance, that is dx. So for example, this much is dx. Okay, and the remaining this one is the deformation. There will be elongation for this bar, deformation, and that deformation will be equal to dou u by dou x into dx. So the what is the coordinate of this point? X plus u plus dx plus dou u by dou x into dx. Okay, so that is the coordinate of this point. And what is the new length of this bar after these two type of displacement? The new length will be equal to the final coordinate minus this n coordinate minus this n coordinate, right? So this will be equal to x plus u plus dx plus dou u by dou x into dx minus x plus u. So minus x plus u in bracket. So this will be the new length of this bar. So here we can cut these two x and u. So we got dx in plus dou u by dou x into dx. This is the final length of the bar. Okay. Then in this, the term dou u by dou x, the term dou u by dou x is called displacement gradient or gradient of displacement. Gradient of displacement. Okay. So this is the gradient of displacement in x direction. So we only consider the movement in x direction. So this is the gradient of displacement in x direction, dou u by dou x. And this dou u by dou x, the displacement gradient is the measure how rapid the displacement or deformation changes through the materials. Okay, the how rapid the deformation occurred on a material. This also represents the unit change in length of a line element. Okay, and this is also a strain. This is also a strain. I will explain how it changes to strain. Next, we are going to calculate the strain on this bar. Strain. So strain in x direction. This is strain in x direction. Okay. What is strain in x direction? This is a new length, right? This is a new length. New length is equal to dou x dx plus dou u by dou x into dx. So new length minus previous length. Okay, that is the change in length. So minus dx. So change in length is equal to new length minus original length divided by original length. That is a strain. Okay, so that is the strain. So here from this, these two terms are cut, and this is dou u by dou x. Or we can say this displacement gradient dou u by dou x, displacement gradient dou u by dou x, this is the strain in x direction. So strain in x direction, epsilon xx can be written as dou u by dou x. Similarly, we can derive the strain in y direction. How? By considering bar in y direction. By considering bar in y direction, apply the same procedure. We got strain in y direction is equal to dou v by dou y. Dou v by dou y. Where the displacement in y direction is equal to v. Similarly, if we consider a bar in z direction, the deformation in z direction, we got the strain in z direction, that is dou w by dou z. Dou w by dou z. Okay, so here u, v, w are the component of displacement in x, y and z direction respectively. So that is the linear strain. Linear strain. linear strain, because this is a linear deformation. So this will be a linear strain in x. This is x direction deformation, this is y direction deformation, and this one is the z direction deformation. Okay, next we are going to calculate the strain, um, shear strain. So this is the linear strain. Next is shear strain. Okay, so for the shear strain, I am considering a rectangular element ABCD, and its dimension in x direction it is dx, in y direction it is dy. Dx and dy are the dimensions in x and y direction. And here in this bar I am applying a shear force. So here I am applying a shear force in this direction, a pure shear condition. Only shear force is applying here and here. Shear force is applying. And I kept this point A as fixed. Okay. So what happened? The body will deform, and this is the deformed shape of the body. Because the point A is fixed, there is no change in position for point A, and the remaining all points will change its position. So this is the deformed position of the rectangle. So this is B dash, this is C dash, this is D dash. Okay, so this is the deformed position after subjected to external shear force. And here the point A is fixed. So the new position of B is B dash, new position of C is C dash, for D it is D dash. Okay, so here what is the length of this BV dash? What is the length of this BV dash? BV dash, the length is equal to dou V by dou X into dx. It will be the length of BV dash, because here from this we already derived the strain in a linear strain, that is dou U by dou X into dx. Dou U by dou X into dx, and in V direction it will be dou V by dou Y. The strain is equal to dou V by the deformation is equal to dou strain is deformation y direction is equal to dou V by dou X, dou V by dou Y into dy. Deformation is y direction, but here it is dou V by dou X into dx. It's not dou V by dou Y into dy. Okay, this is because at point A, displacement in y direction is 0. Here the displacement in y direction is 0. As we move towards B, the displacement in y direction is increasing. Okay, as we move towards B, the displacement in y direction increasing in relation to distance from A. So the variation of this value, the displacement variation in y direction, is with respect to the distance from A. Okay, the distance from A. So that is why we give this is the displacement dou V in y direction, but it's with respect to the distance from A. So that is why it is dou X into dx. Okay. So the variation of displacement is with respect to this dx value. If the dx is small, the displacement is low. The dx is large, then displacement is also will be a maximum. Okay, so it is with respect to dx. Similarly, here what is this? This value d dash, d dash is equal to dou u by dou y into dy. Here the displacement in x dash, in this dash, displacement in x dash, that is why it is dou u. But how this displacement vary? This displacement dou u vary with respect to y, dy. Because here displacement is very low and here it is increases, again it increases. So it vary with respect to y. So that is why it is dou y into dy. Okay, so the angle, initially this angle is BAD. Initially this angle is, just a second. Initially this angle is rectangle, that is BAD is 90 degree. But after deformation we can see this is the angle. The angle is reduced. The angle is reduced. And this change in original right angle is called shear strain. Okay, so this deformation or the distortion in shape is measured in terms of this change in right angle. So the shear strain at point B is equal to, here we have two angles, alpha and beta. We have two angles, alpha and beta. This is alpha angle, and this is beta angle, alpha and beta angle. Okay, this one is alpha and this one is beta angle. And that is the, actually that alpha and beta is the amount of change in rectangle of that point A. So what is tan alpha from this? Tan alpha. Tan alpha is equal to alpha, that is equal to, because alpha value is very small, we can take alpha as tan alpha. So that is equal to B dash opposite side by adjacent side, B dash divided by AB, which is equal to dou V by dou X into dx divided by dx is equal to dou V by dou X. Similarly, tan beta almost equal to beta value, because this beta value is very small, that is equal to d dash by AD is equal to dou u by dou y into dy divided by AD is equal to dy is equal to dou u by dou y. What is the total strain in this xy plane? So that is gamma xy, that is equal to alpha plus beta. That is the total strain, or it is equal to tan alpha plus tan beta. Because alpha and beta are very small, we can take tan alpha plus tan beta. So this is equal to dou v by dou x plus dou u by dou y. Dou u by dou y, dou v by dou x. So this is the shear strain in xy plane. Shear strain in xy plane. This is the component of shear strain in xy plane at the point A. At the point A. Similarly, we can write the shear strain in another plane, YZ plane. So if we do the same procedure on YZ plane, we got shear strain YZ plane, that is equal to dou V by dou Z plus dou W by dou Y. Similarly, in XZ plane, it is equal to dou u by dou z plus dou w by dou x. Okay, so this is the first strain. So this one is second. This is the third strain. Shear strain values. So we got three shear strain values: gamma xy, gamma yz, gamma xz. That is the shear strain in xy, yz and xz planes. And this is the strain displacement relationship. And this is only applicable for small strain only, because we assume it's a very small strain. It's a very small strain in point A. So this equation is only applicable for small strain. And this is called Cauchy's strain displacement relation. Okay, these three shear strain values is called Cauchy's strain displacement relation. And this gives the relation between the strain, this is the strain, and U and W are the displacement. U is the displacement, unit displacement in x dash, and W is the unit displacement in z dash. Okay, so we got three shear strain values in x, y, y, z, and z, x, z plane. Next, we are discussing this Cartesian strain matrix. Cartesian strain matrix. We already derived these three strain values, shear strain values. What are they? Gamma xy, gamma yz, gamma xz. Three shear strain value. And in the previous derivation, we derived three linear strain value. Three linear strain value. Epsilon xx, epsilon yy, epsilon zz. Okay, so epsilon xx, epsilon yy, epsilon zz. Okay, and this gamma xy also can be written as the for xy plane. Similarly, we have yx plane, gamma xy dash, and similarly gamma yx, gamma zy, gamma zx. Have these three other shear strain in that dash shear strain. Okay, this is in xy dash, this is in yx dash. So we have, similar to the stress at a point, we have 9 components of strain at a point. 9 components of strain at a point. And this 9 component can be written in a matrix form, that is the epsilon ij equal to, in a matrix form we can write similar to the shear stress, stress at a point. Instead of sigma xs we write epsilon xx, epsilon yy. The diagonal terms are normal strains or linear strain, epsilon zz. This is gamma xy, gamma xz, gamma yx, gamma yz, gamma zx, gamma zy. This is the strain tensor. Strain tensor. Okay. And here in this gamma xy, gamma xz, all the shear terms in the strain tensor is written in a second order. If you want to convert into a second order terms or tensor, the shear strain terms are halved. These values are halved in order to convert it into a second order tensor. So this will be the new one, that is epsilon xx, gamma xy by 2. So this is halved. Gamma xy is changes to gamma xy by 2, because to convert this stress tensor into a second order tensor, that is why it is changes to gamma xy by 2. So this will be the gamma xz by 2, gamma yx by 2, epsilon yy. Only for shear strain values. We have only the shear strain value yz by 2, gamma zx by 2, gamma zy by 2, epsilon zz. So this is the strain tensor or the strain matrix in Cartesian coordinate. Okay, strain tensor. So here we have 9 components, and again we can apply the equality or similar to equality of cross shear. Here also we can apply the equality of cross shear strain. So gamma xy equal to gamma yx. So gamma xy by 2 equal to gamma yx by 2. We have applied the equality of cross shear in case of stress tensor. Similarly, here gamma xy and gamma yx are same. We already proved all the equality of cross shear, and similarly we can write this also. Gamma xz by 2 equal to gamma zx by 2, gamma zy by 2 equal to gamma yz by 2. So this matrix 9 components is reduced to 6 components. 6 components. So this is the new matrix epsilon xx, gamma xy by 2, gamma xy by 2, gamma xz by 2. Then again here also gamma xy by 2 because both are same. Then epsilon yy, gamma yz by 2, gamma xz by 2, gamma yz by 2, epsilon zz. So here we have only 6 unique components. The 9 components here is reduced to 6 unique components by applying equality of cross shear. Okay, and this we can write in a engineering strain form. Engineering strain form, that is nothing but all are represented in epsilon form. Epsilon xx, epsilon xy, epsilon xz, epsilon xz, sorry, epsilon xy, epsilon yy, epsilon yz, epsilon xz, epsilon yz, epsilon zz. Where epsilon xy equal to gamma xy by 2. Okay, this is in another form. We are written in the engineering strain form. So this is the strain at a particular point. Strain at a particular point. So this is the totality of all strain in possible direction passing through that point P. So that is the strain at a particular point. Okay. Then what is the analogy between the stress tensor and the strain tensor? We develop or derive the strain tensor. This one is the strain stress tensor, and similarly we already derive the stress tensor also. Sigma xx, then shear strain, tau xy, tau xz. So similarly we have a strain tensor, and this is a stress tensor. This is a strain tensor. Okay, so what is the analogy between the stress and strain tensor? The first one is the diagonal element of the stress tensor represent the normal stress. In case of the normal stress, stress tensor, sigma xx, sigma yy, sigma zz. That was the normal stress in the stress tensor. But in case of the strain tensor, the diagonal elements are normal strain. So that is the first analogy. In case of stress tensor, it is diagonal elements are normal stress. In case of strain tensor, it is normal strain. And all other elements, that means off diagonal elements of the stress tensor represent the shear stress. In case of uh, shear stress and tensor, will show. And this is our stress tensor. All the off diagonal elements, are the shear strain values. And here also all the off shear stress values. Here all the off diagonal elements are shear strain values. And but here in this strain tensor, the off diagonal element of the strain tensor are half of the shear strain on a plane parallel to the coordinate plane. So that is important. Here it is not gamma xy, it is gamma xy by 2. But in case of shear strain, shear stress, it is tau xy. It is not tau xy by 2. It is only tau xy. But here it is gamma xy by 2. Okay, so here it is halved. The off diagonal elements. Okay, half of the shear strain on the plane parallel to the coordinate planes. And both the stress tensor and strain tensors are symmetric in nature. This is symmetric in nature. Okay, you know what is a symmetric matrix. So these two stress and strain tensors are symmetric in nature. And the extreme values of normal stress called principal stress are the eigenvalues of stress tensor, and the extreme values of normal strain from this point is given by eigenvalues of strain tensor. You know what is the eigenvalues of a matrix, and the eigenvalues of the strain matrix is the maximum strain, and the eigenvalues of stress matrix is the principal stress or maximum normal stress. Okay, that is also another analogy of the stress and strain tensor. And the transformation rule is equally applicable for both the stress and strain tensor. Transformation rule is applicable. Stress and strain tensors are related to fourth order tensor considering of the property of the material of the body. So these are both are fourth order tensors. So that is the analogy between stress and strain tensor. Next one is planes. Next one is plane stress or plane strain condition. Plane strain condition. We already discussed about plane stress condition. Similar to this plane stress condition, one axis of the body is free from any strain. That is the plane strain condition. So we can write, for example, we consider Z axis is free from any type of strain. Then in this matrix, we can say the epsilon Z is equal to 0. Because in that axis direction there is no strain. We consider that is a zero strain axis. So similarly we can write gamma xz equal to 0, gamma yz also equal to 0. In z direction everything is both normal and linear, and this shear strain is 0. So we can reduce this equation. If these three values are 0, we can reduce this equation. So this is the equation epsilon xs gamma xy by 2. This is equal to 0. Okay, this is equal to 0. And this one is equal to 0. This one is 0. This one is 0. This one is 0. Because all the terms are 0. This contain which is all these are in z direction. So this is the new matrix. New matrix gamma xy by 2, gamma xy by 2, epsilon y. Only 4 components. So initially it was 9 components. By applying the cross shear, we reduce the 9 components into 6 unit components. Again, applying the plane strain condition, we reduce to 4 components. Okay, so this is the strain tensor for a plane strain condition. So next we will do a problem based on this. So this is the problem. The displacement field for a body is given by u is equal to x square plus yi 3 plus zj x square plus 2 minus yk. Determine the strain tensor at the point 3, 2, minus 1. So that is the problem. So here the displacement field is given u is equal to x square plus yi 3 plus zj plus x square minus 2 minus yk. So from this, along with the I, that is the, so this is capital U. It's not small u, it is capital U. Small u, the component x, component or displacement component x dash is along with the I. So the u will be x square plus y. And v is along with the, we know the vector equation ui plus vj plus zk, sorry, wk. So here u will be x square plus y, v is 3 plus z, and w is equal to x square plus 2 minus y. And we know this equation, what is epsilon xx, we already derived this equation epsilon xx. So now epsilon xx is equal to dou u by dou x. Okay, dou u by dou x. So applied epsilon xx is equal to dou u by dou x. Differentiate this with the partial differentiation of x square plus y is equal to 2x. Similarly, epsilon y by dou v by dou y, epsilon z is equal to dou y by dou w by dou z. Apply, differentiate this v with respect to y and w with respect to z. So we both are 0. And what is gamma xy? That is also we derived gamma xy. Gamma xy equal to dou v by dou x plus dou u by dou y. Okay, so gamma, similarly gamma yz is equal to dou v by dou z dou w by dou y. So we know, again partial differentiate this, dou w by dou y can be calculated from this, dou xy, sorry, gamma xy, dou u by dou y, what is, we know what is u, that is x square plus y. So differentiate with respect to y, and dou v by dou x, v is equal to 3 plus z, differentiate with respect to x. Okay, so when we differentiate this with respect to y, we got it is equal to 1, and with respect to x, here there is no x term, so it is 0, so it is equal to 1. Similarly, we can differentiate and find this gamma yz and gamma xz values. This will be 0 and 2x. And from this, we can write the stress tensor matrix. We calculate all these values, gamma xy by 2. And here is very important. Here gamma xy equal to 1. Gamma xy equal to 1. But here you should give gamma xy by 2. That is equal to 1 by 2. Okay, that is very important. Because in our matrix, all the terms, all the shear strain terms are halved. All the shear strain terms are halved. So here write the half of the calculated value, gamma xy by is 1, gamma yz is equal to 0, gamma xz is equal to 2x. Okay, so half of that value. And for the point 3, 2, minus 1, x, y, z are 3, 2, minus 1, then we can apply the x, y, z, and we can apply this value x, y, z in this matrix, and we can find this matrix. So such a similar small problems may ask in your exams also. For simple strain condition, what is the strain tensor value? Such a type of problem may ask in your exams. Okay, so that is about the strain displacement relation and the strain tensor. Strain tensor. So up to this lecture, we have studied about the stress and the strain, the relation. Next year, we will study the relation between the stress and strain in the next lectures. And that is all about this lecture. Thank you.